this talk's all about benchmarking. And the most terrible problem I found with benchmarking is trying to get good results, which is kind of the whole point. I've only got 20 minutes, so hopefully I can convince you in that time that change point detection is a really good tool to have in your tool belt when you're doing benchmarking. So benchmarking and detecting useful results, for me, all comes down to noise. And when we talk about noise, we need some sort of shared understanding. I think everyone kind of gets it in theory, but it helps be a little bit more specific. So when I say noise, what I'm talking about is a large range of possible values you get from your benchmark. If you have like a wide range, I would say that was a noisy benchmark, or it produces noisy results. If you have a narrow range, there's less noise. What this really means is there's a high variability in the results. This is bad because it makes it difficult to figure out when you change things, whether that's caused by your software change you made or your infrastructure change, or it's just symptomatic of the test or the infrastructure as a whole. So visually, this is kind of what I mean. There's a spike on the left, and this is noise. Now, I can only tell you that because I know what these results are. I know how the test was run. If you don't know that, you can't infer that, but just take it from me. This was a benchmark that was run periodically for a number of weeks. I didn't change anything about the software or the infrastructure, and we get this kind of outlier here, which has nothing to do with the thing that I am testing, or the system that's under test. Now, the world is full of randomness, and there's always some change going on, and so that circle of things that you care about is a really important distinction. There's always some things changing, but it's whether it's the system you care about is changing. So if you've run benchmarks offline as opposed to online, so all the results in this are going to be benchmarks that were run sort of outside of production on like a development laptop or something like that. And the reason I make that distinction is because the change point detection techniques that I talk about are all what's called offline techniques. There are online techniques, you can do that, but this talk doesn't really cover that. But there are analogous methods for doing it. So this is a very simple scheduler benchmark that I've run. And pro tip, if you do any kind of benchmarking on your machine, perf stats, not just for collecting performance counters, it's a really good benchmarking tool. If you run it with -n, that's no counters, and -r for repeat, you get a very, very simple but useful benchmarking harness, essentially. So I've run this benchmark 3 times, and as you can see, I get like what I would like, it's pretty different results every time, right? Not change anything, I just run it in a loop 3 times. And this is frustrating and not particularly useful in terms of figuring out like, well, what is the wake-up cost? It could be any of these numbers. But also, so this is like an actual metric reported by the benchmark. Also, the time to run the benchmark varied as well, which is another source of noise. So why are benchmarks so noisy? Really, this comes down to indeterminism. When we build systems, when we design systems today, we design them for peak performance. We don't really design them for stability. So what I mean by that is hyperthreading is a good example. Turbo boost is a good example. People don't like designing systems that have slack or underutilized components. And so what we tend to do is utilize them when they're idle, right? Hyperthreading is a good example of this. You share some CPU features, some parts of the pipeline, you share an L1 cache, but you can't have 2 different cores using that at the same time, right? Or using the same slots at the same time. So you get contention. And a lot of the indeterminism in benchmark results comes from contention at some point of the stack, in the hardware, in the software, usually driven by ramping up the utilization of some shared resource. And what's crucial for this is, unfortunately, because this is how we build systems, you can never really escape this. This is fundamental. And there are things you can do to minimize this. There is a trade-off to be made there. You can spend a lot of time reducing noise in systems. Some of it's well worth it, but at some point you get diminishing returns, and it doesn't make sense to devote any more time into removing that noise. You can never fully remove it, but you can get pretty close. But the upshot is that we need some method of dealing with this noise. So here's another example. This is my favorite example of noise in modern systems, and it's the CPU frequency. I've done benchmarking like this for over a decade. Every 6 months, I forget this. Swear to God. Like clockwork, every 6 months, I will forget the CPU frequency on a system can fluctuate depending on how you've set the the CPU frequency governor, which is the policy basically for the clock speed of the CPU. On this slide, this is the important bit, which is the power save governor will make decisions for the CPU frequency to conserve power. So it's great if you're on a battery on your laptop, not so great if you want repeatable performance benchmark results. Because what it will do is it will scale the frequency up and down. If you go to a higher frequency, you get faster performance, you get better performance, but you use more power. If you go down the scale, it's the other end. You save more power, worse performance. But the problem with this CPU governor is it will move this needle up and down the spectrum based on the load on the system. The load is usually not constant, so depending on how many times you run the benchmark, you'll get like varying results. This is a visual representation of the CPU frequency changing. So this is me running a benchmark on a public GitHub runner. Don't ever do that. And this is why. The CPU frequency, and you have no way of controlling this too because it's a public GitHub runner, right? You can't actually set the frequency governor. But you can see it bouncing around as the test's running. So the test is placing constant load on the machine and the frequency is just going nuts up and down. And what that means is your results will vary, and no matter how many times you run it, you won't get consistent results. You tend to have to do something like averaging, which you'll get this wide range of possible values, which again isn't particularly helpful. So one of the best techniques I've found for handling this noise that we can't ever truly get rid of is using change point detection. It actually comes from the signal processing community. It's been used for decades for various different things. Climate research, fraud detection, things like that. And what it does is it detects shifts in a time series distribution, like permanent or stable shifts. So it doesn't detect outliers, which you would categorize as like a temporary change, but it will detect like underlying changes in a time series distribution. I first learned about change point detection from this paper from MongoDB around 2020. Because I had a similar problem. I was building a benchmarking system at SUSE, the Linux operating system company, and I had this problem which I would run benchmarks for kernel releases, and the results would just be all over the place. And what this paper talks about is using CPD to get a handle on that noise, to find changes in benchmark results, even though you have some noise. And I actually reached out to the authors of this paper. Little tip, if you see a paper, a research paper, and you like the topic and like the thesis, just email the authors. You can also ask them for the paper as well. If you email them, ask them for the paper, it's behind a paywall. Researchers love to talk about things they've published. So I started a company, one of the co-authors of this, and then we went on to publish a second paper, changing a couple of the parameters of the first paper and getting more stable results again. So, as I said, the CPD literature is old, it's decades old, so it's very, very big. It's really, really big. And I'm going to try in a couple of slides to condense all of that literature down and explain it in the next like 60 seconds. So basically the thing that illustrates CPD is you have these three components of any algorithm, and depending on how you implement these, that gives you a different algorithm. But this gives you a map for essentially navigating the different research papers and the literature. So all algorithms need to search through a time series. Then they need to compare points in the time series. And finally, they need to filter out anything that's not statistically significant. The first two steps kind of work in tandem to find what are called candidate change points. The change point is a place in the time series where you get that fundamental shift. And then the last one, the filter mechanism, is basically for discarding things that are not statistically significant, that you don't really care about. So here's an example time series. And if you were to run a hypothetical CPD algorithm on this, you would slice. So this, like the search step, is basically partitioning the time series. They all work a little bit differently. Some of them have windowing mechanisms. But essentially, one of the powers of CPD is it will often do like pairwise comparisons between like all of the points, which allows it to find those permanent shifts. So you partition the time series, and then you search recursively on the left and the right. So let's say it doesn't find any candidate change points on the right, it'll do the left. it finds a candidate change point there. So these lines represent what it thinks are potential places of significant change in the time series. It will partition again and recurse and go on. And then it stops there. So it has 2 candidate change points, basically from this time series. So I would be lying if I said like CPD will solve all your problems. Of course it won't. It helps in some specific circumstances, but it has some limitations too. Because of this comparison between all the data points, that's kind of the power of CPD, is that it isn't perturbed by outliers and one-off historical events, but it does require multiple data points in order to find change points. How many data points? It varies with the algorithm, the library, but I've seen like 5 is pretty typical. So you can need like 5 data points, and then somewhere in those 5 there could be a change, and then it will detect it. If you have 4, it may not. And also, one of the weirdest things about CPD, which makes it difficult to use the offline methods for online detection, like in production, with production metrics that are live, for example, is that there is a lag in the detection. What I mean by that is, if you're collecting results from a CI pipeline, for example, you run benchmarks in that, and you post results every time the CI job runs, you may detect, and you do that every day, say you run a nightly test, and you do it Monday through Friday. On Friday, you may detect a change in performance that was registered on Tuesday. So there is like a lag. And that's because as the algorithm kind of sees the holistic set of results, it can then infer where changes occurred. For offline stuff, like when you're doing a lot of performance testing or you're tracking changes in software, this is fine. It's obviously a lot more difficult for real-time, up-to-the-minute detection, like fraud detection. They use online algorithms for that, which is slightly different. And the last biggest drawback, I think, with CPD in general is because of this, it's the power of the algorithms, and also like what makes it unsuitable for other stuff is because you're doing this pairwise comparison between all the points, it's computationally quite expensive. The best ones, I think, are like ON squared. The worst ones are much worse than that. If you don't have a lot of data, it's probably fine. If you have lots and lots of data, it can get time consuming. I have managed to do this with 100, 200 data points for a single metric, fast enough that you can render it on a website. So you're talking like milliseconds, maybe 100 milliseconds, 200 milliseconds of latency. So it's totally doable. But again, if you had 1,000 data points, that would be pretty impractical. So if you want to try this out, there are a number of projects for this. The signal processing one came from the MongoDB paper. It's written in Python. It's pretty good, especially if you just want to get around, if you just want to start playing with it. I would recommend checking this one out. If you use benchmark.net, if you do like .NET development, Perfilize is actually used for that, and it uses change point detections algorithms for finding changes. There's also Hunter. So this one came out of the MongoDB one came out of the Mongo paper. This project came out of the Hunter paper that I co-authored. Under the hood, it uses the MongoDB library for a lot of the maths and the matrix calculations. But it has integration with GraphI and CSV files and just a little bit of syntactic sugar on top. And also, it replaced one of the comparison. I talked about those 3 components of the CPD algorithms. It replaced the comparison function with a student's t-test, which is a lot faster than what's in the MongoDB library. And Ruptures is a Python CPD library that actually, it has nothing. So the first 3 were really for performance, benchmarking, and so on. Ruptures isn't actually specific for performance. It's just a general purpose Python library that has many CPD algorithms. And I think it goes along with this paper that's referenced here, the offline survey paper. So just to recap, there's I know there was a whirlwind tour. I've left enough time for questions if anybody has questions. Just to recap, so you can't ever truly escape noise. You can minimize it, but there are diminishing returns with that. Change point detection is, I think, a good tool in your toolbox for doing benchmark analysis and offline performance test analysis. And there's a lot of cool open source projects that people have taken care of implementing a lot of the maths behind this So you can just kind of plug your data in and see if you get interesting results. And there's enough of them to kind of contrast and compare and try different ones out. I'll show these slides, or the slides will be shared. So there's a couple of survey papers for different algorithms for this, and there's the MongoDB one and the Hunter one at the bottom. Thank you for your time.